Hi, welcome to the new episode of Radio Data Podcast. Today we will discuss modern data platforms. What makes a data platform modern, what makes it different from the traditional solutions built earlier, and how the data platforms evolve in general. We won't deep dive into any particular tool or framework, but we'll try to focus on visible trends and try to summarize some big changes that we could see. I hope you will enjoy this podcast and stay with us. So let's get started. I think one of the most important trends that can be observed is the adoption of best practices from the software development domain. Historically, it was quite common to use either commercial enterprise tools to draw and implement ETL jobs or write custom SQL queries and execute them from stored procedures right in the database. The limitation of such an approach was that it was difficult to implement standard ways of working known to software engineers, like testing, support for separate environments that have synchronized code deployment, and so on. In a modern data platform, ETL jobs are code, and all the practices used to build reliable software are used to maintain high quality of the data. Tests should be used to check the developed transformations, build should be triggered automatically, and code should be deployed using CI/CD pipelines. It's good to have infrastructure as a code to make sure the code repository contains the full definition of the environment and can be easily deployed on different stages like sandbox, development, or production. Fortunately, there are frameworks which promote this way of working. dbt, Data Build Tool, is a good example. In that framework, data pipeline is defined as a series of transformations. Each of them is expressed in SQL. Since the whole project is a code and YAML config files, we can benefit from code review, deployment on multiple environments, and CI/CD pipelines. Wide variety of tests is also supported, starting from simple checks on column values like unique values or not null, to more complex cases where we run our transformation on test data. By the way, at GetInData we use dbt in many projects, and we have open sourced some extensions which make, for example, scheduling with Apache Airflow much easier, or add command line interface to handle data project. Large data volumes, so typical for data platforms, usually require also significant computing resources. And in many cases, it's not trivial to plan the capacity in advance. There are many projects, different users, and it's hard to predict what will be the actual workload for our system. It's even more difficult for startups or companies that are scaling up because expected workloads are simply unknown. Business changes, and this will definitely have an impact on the computing. Therefore, more and more systems provide serverless or close to serverless ways of using the data platform. Google's BigQuery is a good example. We are built by the volume of data read from the storage while executing our queries. AWS Athena or AWS Redshift serverless offering also work in a similar fashion. Snowflake has an idea of computing clusters that are decoupled from storage and can be started up within a second and shut down automatically when not used. The great benefit of such a serverless model is that it lets start small and deploy fast without committing to estimated capacity. We can deploy our data platform on some small scale, prove that it works, show results to the business, and then scale up to full capacity. These serverless possibilities are definitely one of the trends visible in data platforms. But the serverless is not the only change. Cloud has been a revolution for the whole industry, and it is one of the trends that we can observe in data platforms as well. Pre-cloud data platforms were usually built around well-defined technology stack, no matter if it was an enterprise data warehouse solution or open source Hadoop distribution. It often was challenging to accommodate non-standard use cases. Sometimes it would require extending the stack and team, in other buildings a separate system along existing solution. And that's the moment when a change happens. Having a cloud data platform, we have access to other services from the cloud provider portfolio. This makes the integration with other systems much easier. I could see that especially in situations where products built on a data platform, let's say recommendations or customer segmentation, needs to be shared with other systems, with other teams or backend services. In on-premise deployments, this usually requires much more effort. In many cases, finding new tools that will be used to share or host the results, or extending the team. In the cloud, we are free to use services that are already in place, and moreover, engineers familiar with the cloud usually know how to use them. Collaboration between data and backend team is much easier in such setups. From the business perspective, delivery time of new features can be much quicker. So, is the new data platform batch or streaming platform? I think there is no one size fits all. Usually data warehouses run in daily batch mode. There are still many cases where such approach is sufficient, but on the other hand, there are many streaming use cases like fraud detection, real-time customer segmentation, or recommendations for customers. So I think there is no one size fits all. What's important is to remember that data platform should have a flexibility to accommodate different workloads. Cloud environments make it often possible with ease because we have already rich portfolio of services available from the cloud provider. In case of AWS, for example, we can use managed Kafka clusters to handle streaming data and process them in AWS EMR cluster running Spark streaming or Flink application. If we prefer to have a service that handles streaming and processing at once, we can use AWS Kinesis and use simple SQL-like expression to do the aggregation. All of this can happen in parallel with existing batch processing that operates on S3 and, let's say, EMR clusters. So the key point here to remember is that we are not aware of all the use cases that will be relevant, and it's highly desired to have the flexibility to be able to meet the business requirements that will be crucial at some point of time. So instead of focusing on single use case, it's better to have the flexibility of running multiple workloads. In a fast-changing world of computer science, it is quite funny that the language that was developed in the mid-1970s still is regarded as a universal data access and data transformation language. Even more, many of the new frameworks that are introduced end up sooner or later with SQL support, as it is difficult to promote new products with a custom language. SQL is still taught at the universities, and you will find it as a top requirement in jobs advertisements in data domain. And it may be the only common language used by engineers, data scientists, analysts, and business in your organization. Using a well-known language has a huge impact on data democratization. Low entry barriers mean more people can test their hypotheses, analyze results, and promote data culture within the company. With SQL support, it's easier to encourage more people in active ETL development with only little support from data engineers. It's also very important when concepts like data mesh are gaining popularity with such decentralized architecture and decentralized data ownership. It's important to provide low entry barriers and easy access to the data platform. So to summarize, both traditional and modern data platforms support SQL, and it doesn't seem to change. SQL popularity is beyond question, but it doesn't mean there are no changes in this area. It's quite common that we can extend the core functionality of a language by user-defined functions or UDFs. And modern data platforms quite often let us define the functions not only in SQL, but in other languages or even call external systems. In Snowflake, for instance, this functionality is called external functions, and it's a great option to have more advanced logic deployed as, for example, AWS Lambda function, or even HTTP endpoint, and then call it directly from Snowflake. Such layout greatly enables more advanced use cases which would be very difficult to implement in pure SQL functions. Other interesting extension that affects SQL are templates in dbt. As we mentioned before, dbt defines the transformation as a series of SQL queries that are used to create tables on different stages of our pipeline. But it doesn't need to be just pure SQL. We can use Jinja templates to include more advanced logic that will make the development easier. Imagine that we have very wide tables with tens or hundreds of columns, and instead of enumerating all the columns one by one, we can define a list that will be reused in many expressions in our queries. We can use for loops or even define macro, for example, to embed some common logic like complex case statement that will be used in different queries. So it is still SQL, but thanks to different extensions like external functions or templating, we have much more flexibility when defining our pipelines, and it's a great advantage of modern tools. To summarize, there are some trends which affect the whole IT industry, like cloud computing, serverless approach, infrastructure as a code, and they have also influenced the shape of modern data platforms. One of the most important things is to make sure the platform supports efficient development techniques that prove to be successful in other areas, like testing, CI/CD, code reviews. Technological advances in cloud computing allow data platforms initiative to start easily without over-provisioning in advance. Cloud-native approaches give us also the opportunity to improve compliance and cost optimization. With ever-popular agile approach to software development, modern data platform must also be flexible enough to handle different workloads, even those unknown at the beginning. Last not least, are there any ideas that we can learn from traditional old data platforms that were built years or decades ago? I think it's still worth remembering that in the end it's not just the platform, but the data, and we are just as good at building the platform as reliable and useful the results are. That's all for today. Thank you for listening to this episode. I hope you enjoy it. Please remember to visit our blog at getindata.com/blog to find more content on data, analytics, machine learning, cloud, and of course, data platforms. Thank you.